This session demonstrates generation of binary differential phase shift keying and the detection of this binary DPSK signal. Course objective is to test the performance of binary differential phase shift keying system by simulating the non-quantum detection of binary DPSK requirement MATLAB survey. Differential phase shift keying is a form of a correlation in which the data is conveyed by changing the phase of the carrier wave. In DPSKs, instead of encoding information into absolute phases, the information is encoded using phase differences between successive signal transmission. So this shows the DPSK signal, that is differential binary phase shift keying. So in this binary, one is transmitted by adding 180 degree to the current phase, and binary 0 is transmitted by adding 0 degree to the current phase. So therefore we can see when the data bit is high, there is a phase, there exists a phase difference. So here also there exists a phase difference when the data bit is 1 or I. So when the data bit is 0, there is no phase differences. So this figure shows the DPSK modulator in which the binary input data is provided to one of the input of the XNOR gate, and the other input of the XNOR gate is provided by the binary data with 1 bit delay. So the output of the XNOR gate is provided to the balanced modulator, so in which the carrier signal is provided to this balanced modulator in order to obtain the DPSK signal. Figure here shows the DPSK demodulator. DPSK signal is provided as the input to the balanced modulator, and the delay of this DPSK is provided to the balanced modulator. The output of the balanced modulator is provided to the low pass filter, which eliminates the high frequency components, and the output of the low pass filter is provided to the shaper, so which acts as a comparator. It acts as a comparator. It is a decision device. It acts as a decision device in order to recover the binary data. The algorithm to generate the DPSK signal by using MATLAB code. So in order to generate the DPSK signal, first we need to generate a carrier signal like a message. So perform a differential encoding for the signal. So encoding signal in order to get the polar form. So then this encoded signal, differential encoded signal is multiplied by the carrier signal to get the DPSK modulated signal. Then plot the binary data, carrier signal, and the DPSK modulated signal. So in the demodulation process, perform the correlation of the DPSK modulated signal in order to obtain the decision variable signal. Make decision on the variable x to get the demodulated binary data. If x is greater than 0, then the demodulated signal is represented by 1. Otherwise, it is represented by 0. Plot the demodulated data bits. Procedure: in order to run the code, open the MATLAB version. First open the new file and enter the program and save it. Add the path to the location of the file in the system. Compile the program and check for any error and debugging it and observe the waveform. So this is the MATLAB code. First open the MATLAB version. Go to new script and write the code and save the code. So it has already been edited and it has been saved. So here in the code, so first we need to generate the carrier signal. So dB represents the bit duration. So we have time axis from 0 to dB, which is having a sampling set dB by 100. So this is a carrier frequency which is given as TC represents the carrier signal, which is given by square root of 2 pi dB into sine 2 pi fct. So next generate the message signal. The number of bits n equals to 8. Here the 8 bits are provided. That is 10110001. So then here the differential encoding is performed. So in which the previous bit is it's odd with modulated with that of the uh, previous bit is modulated with that of the present bit. So M mod filter. So one this is the bit and the previous bit is modulated, and here the demodulation process takes place. So in which so here it is converted to a polar form. The differential encoded bits are converted into a polar form. It is ones and minus one. So next that is multiplied by the carrier in order to get the DPSK signal. Then the message signal and the carrier signal and the DPSK signal are plotted. So next is to demodulate the DPSK signal. So this performs the correlator function, and in order to obtain the variable x on the x, the decision is taken if x is greater than 0, then the demodulated signal is represented by 1, otherwise it is represented as 0. Once and the demodulated data bits are plotted. So next run the program. So this figure shows the binary data bits. So this is the differentially encoded bits which are in the polar form. In the polar form, +1 or -1. So here this shows the carrier signal. So you can see there is a change in the binary data bits. It is represented by 1. When there is no change in the previous and the present data bit, then it is represented by -1. So this is 1 0 represented by 1. 0 1 it is represented by 1, and 1 1 it is represented by -1. So 1 0 it is represented by the -1. So 1 0 is represented by -1, 0 0 1, 0 1. This is 0 1 is represented by -1. So then it is multiplied by the carrier signal. So when it is -1, so there is a phase shift here. So then you get the demodulated detector, so which is equivalent to that of a transmitted binary data bits. So this is about the DPSK signal. Thank you.